In this section I'm going to talk about continuity, but before I do that I'm going to first derive the equations for volumetric flow rate and for mass flow rate, and then talk about how they relate to continuity. So we're just going to consider this pipe here for both the volumetric flow rate and for the mass flow rate. And this pipe has a constant cross-section area A, and the fluid flow along this pipe, the velocity is C. Okay, and we're first going to consider the volume of liquid which is moving along this, flowing along this pipe per second. Okay, so in 1 second we have a length of fluid denoted L, okay, which is passing our datum here. Now the volume of fluid in the element is the area of the cross-sectional pipe times by the length, okay, and the velocity of the fluid, the velocity of the fluid will be the time that it travels that length. The distance that it travels, which is L in this instance, divided by the time that it takes, delta t. So C is distance over time. Now the volumetric flow rate is defined as the change of volume with time. Okay, and so from our definitions on the previous slide, the volume we said is AL and the time is delta t, and L over t is the velocity. So the volumetric flow rate can be defined as the area, the cross-section area, times the velocity through that cross-section area. And just note that the units here are meters cubed per second. So it's a volume, meters cubed, over time, so per second. Now we're going to do the same thing. So we've got the same pipe, the same constant cross-section area, and the fluid is flowing at the same velocity c along this pipe, and we have this same segment of fluid here. But here we're going to consider the mass of the fluid, not the volume. Okay, and the mass, as we know, is related to density. So the mass is equal to the density times the volume. And the volume, we've already said, is the cross-section area times the length. The velocity of the fluid is unchanged, so the velocity c is the distance that fluid travels in the time that it takes to do it. So the mass flow rate, in the same way that the volumetric flow rate was volume over time, the mass flow rate is mass over time. And the mass, we've just said, is density times area times the length all over the time. And as again, remember the length over time is velocity. So for the mass flow rate, that can be defined as density times the area times the velocity in which it's flowing through that area. And notice here the units are kilograms per second for mass flow rate. So this leads us neatly onto the continuity equation. So if we consider this pipe, which has a inlet, we consider plane 1 and the inlet, and we can see that this diameter is smaller than the diameter at the exit of our pipe at plane 2. So, and then there's a gradual increase in diameter between the two. And obviously we've got the mass flow rate flowing into the pipe is subscript 1, and so just to point out that the dot above the m means with respect to time, so it tells you that it's a flow rate because it's the mass divided by the time, so it's with respect to time. And coming out of our system we have the mass flow rate subscript 2. So the fluid enters plane A, so which has a given cross-section area, subscript 1, a given density and velocity, and therefore, as we know from the previous slide, the mass flow rate into the pipe is rho AC. Okay, all with respect to the inlet conditions. And likewise, if we know the values for the inlet, we can also work out the mass flow rate at the exit. So when the fluid exits the pipe, okay, with a larger cross-section area, A2, which is different to the inlet, the fluid also has a given density, and it's the same, but we'll come on to that in a minute. So it has a given density and velocity at the exit. So the mass flow rate at the exit, or the mass flow rate at plane 2, is equal to rho AC at the conditions that's relating to the exit conditions. But for incompressible flow, you can basically kind of say what goes in must come out, okay? So if we treat this fluid as compressible, so if it's a liquid, remember I said that liquids we can effectively treat as incompressible. Gases we certainly can't. Gases are compressible, but for liquids, for most of the time, for most applications, we can consider them incompressible. So what that means is if we're forcing the liquid into here, eventually it's going to fill up. So if we try and put any more in, we can't fit any more in, it can't squish together anymore because, well, it can't squish together at all because it's incompressible. So if we put some more in, some more has to come out, okay? So that's why when you're considering incompressible flow, what goes in must come out. So therefore, if what goes in must come out, then the flow rates, the mass flow rates must be the same, okay? So so we've got this relationship here. So if the mass flow rates are the same, then the density density times the area times velocity must also be the same as well. And however, if we said this is incompressible flow, then the densities won't change because we've got the same fluid flowing down this pipe. So the density here must be the same as here if it's incompressible. So if the densities are the same, we can basically cancel them from this equation. And what we therefore have then is that the densities cancel, so we've got the area times the velocity are equal to each other. And remembering that the area times the velocity is the volumetric flow rate. So the mass flow rates are the same, and if it's compressible, then the volumetric flow rates are the same. And just be very cautious here. It's not that the velocity is the same, it's the volumetric flow rate that stays the same. So you can see here, this has got a small area, and this has got a large area. So if A is smaller than, so if A1 is smaller than A2, then C1 must be bigger than C2 to maintain this continuity. Yeah, so do you see that the actual velocities will change, but the volumetric flow rate and the mass flow rate will all remain constant. So that has some, another application of this is looking at branch pipes, which is what you can get in a lot of industrial applications. On the last slide, we just considered one inlet and one outlet, but you might end up with a very complex system. If you're looking at a water network pipe system or something like that, then you might have multiple branches. But again, the same equations hold. Because it's incompressible, if you're dealing with liquids, you're dealing with incompressible flow. So what goes in must come out. So if we look at our system here, we've got one inlet and that's branching into these two smaller outlets. So what goes in, M1, and what's coming out, M2 and M3, these two mass flow rates. And so some of these has to equal that. And if it's incompressible, then and if it's the same fluid, then the densities will also be the same and they cancel. So also the volumetric flow rates, the sum of what goes in, some of the volumetric flow rate going in would also be to the sum of the volumetric flow rate on the way out. Okay, that concludes this lecture. Thanks for listening.